Somewhere out there, drifting through the dark and quietly steering the galaxies, may be an object that is older than the Big Bang. Not older in some loose, poetic way. Older as a physical fact, a black hole that formed in a universe before ours and survived the fire that made this one. That is not a fringe daydream. It is a serious, published proposal, and the James Webb Space Telescope has handed us the observations that make people take it seriously. So get yourself comfortable and settle in. Because tonight, we are going to ask whether the beginning was really the beginning, and what Webb keeps finding at the edge of time that refuses to fit inside it. Part 1. The number that shouldn't exist. There is a number that came out of the James Webb Space Telescope that, taken at face value, should not be allowed to exist. When astronomers pointed the most powerful eye humanity has ever built toward a handful of faint smudges near the very edge of the visible universe, and then fed the light from those smudges into their models, the models handed back an age. Not for the light, but for the stars inside those galaxies, and the age that came back was somewhere between 900 million and, in the most extreme fits, 2 billion years. That would be an unremarkable number for a galaxy in our own neighborhood. The trouble is where these galaxies were sitting in time. These were objects at a redshift of around 8, which means we are seeing them as they were when the universe itself was only about 600 million years old. Hold those two numbers next to each other for a moment, slowly, the way you would hold two puzzle pieces that refuse to fit. The stars inside these galaxies were being measured as older than the universe that was supposed to contain them. If you read the result literally, with no caution and no apology, it says that some of these stars began to shine several 100 million years before the Big Bang. Let that settle, because it is the strangest sentence in modern cosmology, and we are going to spend the next 2 hours earning the right to understand it. Either one of the most expensive and precise scientific instruments ever flown is badly wrong about what it is seeing, or the story we tell ourselves about the beginning of time has a crack running through it. Those feel like the only two options: a broken telescope or a broken beginning. And yet, by the end of this, you are going to see that the truth is stranger and more interesting than either of those clean possibilities, because the real answer lives in the space between them. This is what the title of this video is really pointing at. The phrase, something that predates the Big Bang, has two completely different meanings, and almost everyone who hears it collapses them into one. There is the cheap meaning, the embarrassing meaning, where the telescope simply measured something wrong and the impossible age is nothing more than a mistake in the arithmetic of starlight. And then there is the expensive meaning, the one that keeps a certain kind of physicist awake at night, where the universe genuinely contains structure, objects, even whole histories that were inherited from a time before the moment we call the beginning. The entire journey we are about to take is really a journey across the distance between those two meanings, from the cheap one to the expensive one, and the remarkable thing is that the distance is shorter than you would think. To feel why any of this matters, you have to appreciate how solid the number 13.8 billion years actually is. The age of the universe is not a guess scrawled on a napkin. It is one of the most cross-checked figures in all of science, arrived at from completely independent directions that have no business agreeing and yet do. The faint heat of the early universe, measured by satellites mapping the oldest light in the sky, points to it. The ages of the oldest star clusters in our own galaxy point to it. The way the universe expands, measured by climbing a ladder of distances out into space, points to it. When numbers from such different methods land on the same value, you tend to trust the floor you are standing on. So to find something that appears older than that number is not like finding a minor accounting error. It is like feeling the floor flex under your weight in a building you were promised was solid rock. Over the next 2 hours, you are going to meet a small cast of objects and ideas and I want to introduce them now so you know who is walking with us. You will meet a galaxy at the absolute frontier of what light can show, so distant that its glow has been traveling toward us for more than 13 billion years. You will meet spiral galaxies, fully formed and elegant, sitting in an era when spirals were supposed to be impossible. You will meet a single star, much closer to home, that once carried this exact same curse of seeming older than everything around it, and you will learn how that curse was lifted. And you will meet a physicist who looked at all of this and concluded, quite seriously, that the universe is nearly twice as old as the rest of us believe. I want to make you a promise, the kind a fellow traveler makes rather than a salesman. We are not going to hide the embarrassing meaning from you to keep the mystery alive. We are going to walk straight into the debunking ourselves, out in the open, and take it apart honestly, because the most fascinating part of this whole story is not the headline. It is what is left standing after the headline has been demolished. The literal claim that stars formed before the Big Bang is, in the cleanest cases, going to fall apart in our hands. And then we are going to look down at the rubble and notice that something is still moving in it. Think about what we are actually doing here, because it is worth a moment of quiet appreciation. The light we are talking about left its source before the Earth existed, before the Sun existed, before almost anything you could name had taken shape. It crossed an expanding ocean of space for over 13 billion years, growing fainter and more stretched the whole way, until a 6.5-meter mirror coated in a whisper-thin layer of gold, floating 1.5 million kilometers from our planet, finally gathered it in. We are not looking at the early universe. We are catching the last exhausted photons of it as they arrive, like reading a letter that took so long to deliver that everyone who wrote it has been gone for an unimaginable span of time. There is something worth pausing on before we go further, which is why a result like this lands so hard in the first place. We are, as a species, deeply attached to the idea of a beginning. It organizes everything. A beginning gives time a direction, gives cause a place to start, gives the whole grand sequence of stars and planets, and life a first page to point back to. The number 13.8 billion years is not just a measurement to us. It is the edge of the map, the place where the questions are supposed to stop because there is nothing on the other side to ask about. So when a telescope returns data that seems to reach past that edge, it is not only a scientific puzzle. It touches something older and more uneasy, the suspicion that the edge of the map might not be the edge of the territory. I should also be honest with you about what kind of journey this is, because it is not a tidy one. We are not going to march from a question to a single clean answer and shake hands at the end. The honest shape of this story is a question that gets debunked, and then refuses to die, and then splits into several rival answers that contradict each other, none of which has won. If you came for certainty, I cannot give it to you, because the people who actually do this work do not have it either. What I can give you is something better than false certainty, which is a clear-eyed tour of a genuine mystery, told without exaggeration and without flinching from the parts that deflate the hype. That, in the end, is more thrilling than any tidy answer, because it is real. So get comfortable, because this is going to be a long, slow walk out to the edge of time, and the pace is the point. The drama here does not come from anyone shouting. It comes from facts laid quietly side by side until the pattern they make becomes impossible to ignore. And the very first thing we have to understand, before we can judge whether any galaxy is truly older than the universe, is something deceptively simple. We have to understand how you even measure the age of an object you can never visit, never touch, and never see as anything more than a smear of ancient light. Because hidden inside that measurement is a trap, and almost everyone falls into it. Is less than break time equals 1s, is greater than number, part 2. How you weigh the age of starlight. You cannot read a galaxy's age off a dial. There is no clock on it, no birth certificate, no ring you can count like the rings of a tree. Everything we know about how old a galaxy is, we have to reconstruct from a single thing: the combined light of all its stars arriving together as one faint glow. That glow is the only evidence we will ever have. And learning to read it is a craft, one with a beautiful logic and a dangerous blind spot. And you need to understand both before you can decide whether to trust a number that says something is older than the universe. The first piece of the craft is redshift, which you can think of as the universe's odometer. As the universe expands, it stretches the light traveling through it, pulling the waves longer, sliding their color toward the red end of the spectrum, and then beyond it into the infrared. The more the universe has expanded since a beam of light set out, the more that light has been stretched by the time it reaches us. So when astronomers measure how stretched a galaxy's light is, they are really measuring how long that light has been traveling, and therefore how far back in time they are looking. A higher redshift means an earlier epoch, a younger universe, a moment closer to the beginning. When you hear that a galaxy sits at redshift 8 or redshift 14, that is shorthand for how far into the past you are staring. This is also the reason the James Webb Space Telescope can do what no telescope before it could. The first galaxies poured out most of their light as ultraviolet and visible glow, the ordinary colors of hot young stars. But after that light has been stretched across more than 13 billion years of cosmic expansion, all of it has slid out of the visible range entirely and into the infrared. To our eyes, and to the older telescopes built to see the colors our eyes see, the cosmic dawn is simply invisible. It is not too faint. It is the wrong color. Webb was built specifically as an infrared eye, chilled to within a few degrees of absolute zero so its own warmth would not blind it, precisely so it could catch that stretched and reddened light and bring the first galaxies into view. Without that choice, this entire mystery would still be sitting in the dark, unseen. Now we come to the second piece of the craft, and this is where the danger lives. Once you have a galaxy's light, how do you turn it into an age? The method is called spectral fitting, and the idea behind it is elegant. Different stars shine with different colors depending on their age and temperature. Hot, young, massive stars burn blue and die fast. Cooler, older stars glow red and linger for billions of years. A whole galaxy is a mixture of these, and the exact combination of colors in its combined light is a kind of fingerprint of its history. So astronomers take the light, compare it against enormous libraries of modeled stellar populations, and ask a single question: which mixture of star ages, assembled in which order, best reproduces the light we actually see? Whatever mixture wins is your best guess at the galaxy's history and age. And here is the trap, the thing that turns this elegant method into a minefield at the edge of the universe. Several completely different physical situations can produce almost the same fingerprint of light, which means the method can be fooled. The biggest culprit is dust. Cosmic dust, the fine soot of dead stars, absorbs blue light and lets red light pass, so it reddens whatever is behind it. A young galaxy full of hot blue stars, seen through a veil of dust, can produce light that looks remarkably like an old galaxy full of cool red stars. The fitting routine sees red light and reasonably concludes old stars, when the truth is young stars hiding behind a curtain. The second culprit is the rhythm of star formation itself. We tend to imagine galaxies building their stars at a steady pace, but the early universe was violent and uneven, and galaxies formed stars in sudden bursts, going quiet and then erupting again. If a galaxy has an old underlying population of stars, with a fresh burst of new ones layered on top, the combined light becomes genuinely confusing to interpret. The bright new burst can dominate the colors, or the old base can, and the age you recover depends enormously on assumptions you cannot directly check. Picture what you are really being asked to do. It is like standing across a crowded room and trying to estimate the average age of everyone in it, except you cannot see individual faces. You can only see the single blended color of the whole crowd, photographed through tinted glass, in a room where some people are wearing far brighter clothes than others. You would make your best guess, but you would not bet the foundations of physics on it. And yet, at the edge of the universe, a guess like that is sometimes all we have. This is exactly why the phrase older than the universe is so easy to produce by accident. Push the dust assumption one way, push the star formation history another way, and the model will happily hand you an age of 2 billion years for a galaxy that is actually a fraction of that. The number is not a lie. It is the honest output of a method that has been pushed past the edge of what it can reliably do. The difficulty is not getting an impossible age. The difficulty is being sure, afterward, that the impossible age was the mistake and not the message. It is worth dwelling on just how little information we are working with, because it shapes everything that follows. When a galaxy near the dawn of time appears in Webb's detectors, it is often only a handful of pixels, a small smudge of light gathered over many hours of staring at a single patch of darkness. From that smudge, astronomers must extract a distance, a mass, an age, a chemistry, a history. It is one of the most heroic acts of inference in all of science, squeezing a whole biography out of a few photons that have been traveling since before the Earth existed. And precisely because the inference is so heroic, it is also fragile. Every assumption that goes into the models about how stars age, how dust behaves, how galaxies build themselves, becomes a lever that can swing the answer. Change one assumption, and the same smudge can tell two different stories. This fragility is not a flaw in Webb. Webb is extraordinary, the most capable instrument of its kind ever built. The fragility is in the nature of the problem, in the simple fact that we are trying to read the early universe from the faint, stretched, exhausted remnants of its light. No telescope, however magnificent, can fully escape that. So when you hear a confident headline about the age or mass of a galaxy at the edge of time, the appropriate response is not to disbelieve it, but to remember how many careful assumptions are holding it up, and how a better analysis tomorrow might move the number considerably. We are reading the universe's first chapters through frosted glass, and we should never forget the glass is there. There is one more wrinkle, and it matters more than you might expect, so hold on to it. Many of these early galaxies have a black hole at their center, and in the early universe, those black holes were often feeding furiously, swallowing gas that heated up and blazed before it fell in. That blaze of light from around the black hole gets mixed into the galaxy's total glow. To a fitting routine that assumes all the light comes from stars, that extra brilliance reads as extra stellar mass, making the galaxy look heavier, more built up, more mature than its stars alone would justify. So even the apparent size and weight of these galaxies, not just their ages, can be inflated by something that has nothing to do with stars at all. So before we trust any of Webb's most shocking ages, we should sit with how fragile the measurement really is. We are reading a fossil of light, stretched and dimmed by a journey longer than the age of the Earth, and asking it questions it was never designed to answer cleanly. None of this means the impossible galaxies are fake. It means we should be humble. And humility, in this case, has a name and a history, because astronomy has been fooled by exactly this kind of impossible age before, not in some distant galaxy, but in a single bright star sitting practically in our own backyard. To understand how badly Webb might be fooling us, we first have to meet the star that fooled everyone a generation ago. Is less than break time equals 1s, is greater than number, part 3, the ghost of the Methuselah star. The story I am about to tell you happened around the year 2000, and it is the closest thing astronomy has to a ghost story, because the same ghost has now come back wearing a much larger costume. There is a star, not far from us at all by cosmic standards, sitting just a little over 190 light-years away in the direction of the constellation Libra. Its catalogue name is HD 140,283, which is the kind of name only a database could love, so astronomers gave it a nickname that tells you everything. They called it the Methuselah star, after the figure in scripture said to have lived nearly 1,000 years. They called it that because, when they first measured its age carefully, the number came back impossible. The early estimates, built on distance data from a satellite that mapped the positions of stars, suggested this single star could be as old as 16 billion years. 16. The universe at the time was understood to be about 13.8 billion years old, exactly as it is now. So here was a star, bright and close and thoroughly studied, that appeared to be older than the universe by more than 2 billion years. This was not a faint smear at the edge of creation where every measurement is a struggle. This was a star you could point a backyard telescope at, a star in our own galactic neighborhood, and it was carrying the same curse we are now seeing on Webb's most distant galaxies. The thing that should contain it was younger than the thing itself. What made the Methuselah case so instructive is that it was not the work of careless people, and the impossible number was not the product of sloppiness. The astronomers who first dated the star were careful and competent, using the best data available to them at the time. The trouble was that the best data available was not quite good enough, and small uncertainties in the inputs, the distance especially, fed forward into a large uncertainty in the age. This is the recurring shape of nearly every older-than-the-universe scare. It is rarely a blunder. It is almost always a difficult measurement, done honestly, pushed slightly past the precision the data could actually support, producing a number that looks shocking until better precision arrives. The lesson is not that astronomers are foolish. The lesson is that the universe forces them to work at the very edge of what their tools can do, and at that edge, impossible numbers are an occupational hazard. For a while, this was a genuine scandal, the sort of result that gets whispered about at conferences. A star cannot be older than the cosmos that made it, any more than a wave can be older than the ocean. So either the age of the universe was wrong, or the age of the star was wrong, and both numbers were supposed to be reliable. It had exactly the shape of the problem we are wrestling with now, just shrunk down to a single nearby point of light. And the way it was resolved is the most important lesson we will carry with us through everything that follows. The resolution did not come from some grand revolution in physics. It came from doing the measurement better. Astronomers went back and refined everything they could about the star. They pinned down its distance more precisely, because if you get the distance wrong, you get the brightness wrong, and if you get the brightness wrong, you get the age wrong. They looked carefully at its chemistry, and they found something that mattered enormously. This star had an unusually high ratio of oxygen to iron, and the amount of oxygen a star contains changes how astronomers calculate how long it has been burning. When all of these refinements were folded in, the age came down. It settled at around 14.5 billion years, with an uncertainty of roughly 800 million years in either direction. Now, do the simple arithmetic that dissolved the ghost and notice how gentle it is. 14.5 billion years, minus that 800 million years of uncertainty, gives you 13.7 billion years. And 13.7 slides comfortably back inside the age of the universe. The star was not older than the cosmos after all. It was an extremely old star, one of the oldest we know, born not long after the beginning, and it had simply been measured with enough leftover uncertainty to make it briefly appear to break the rules. The impossible age did not survive contact with better data. It evaporated, quietly, the way most impossible things in science eventually do. This is the cautionary tale we have to keep in our pocket for the rest of this journey. Older than the universe is a sentence astronomy has written before, in confident ink, and then had to erase once the measurements sharpened. The Methuselah star did not predate anything. It was a measurement still settling into focus, and when the focus arrived, the paradox simply was not there. Every instinct, trained by that episode, tells us to expect the same ending for Webb's impossible galaxies, and that instinct is healthy. It is the voice of a discipline that has been embarrassed before and learned to be careful. There is a second lesson hiding inside the Methuselah story, and it is more encouraging than the first. Notice that the paradox was not resolved by ignoring it, or by shouting it down, or by pretending the original measurement had never happened. It was resolved by taking it seriously enough to measure better. The astronomers did not decide in advance that the star could not be old and force the data to comply. They followed the number where it led, found it troubling, and then did the patient work of sharpening every input until the truth came into focus. That is the difference between a healthy skepticism and a closed mind. A healthy skeptic does not refuse to look at impossible things. A healthy skeptic looks at them very hard, precisely because they are impossible, and keeps looking until either the impossibility dissolves or it survives. Both outcomes are valuable, and we cannot know in advance which one we will get. So when we turn to Webb's galaxies, we are going to do exactly what was done for Methuselah. We are going to take the impossible numbers seriously, follow them honestly, and then sharpen every input we can, watching to see whether the impossibility evaporates the way the stars did, or whether, this time, something stubbornly remains. The Methuselah star is not just a cautionary tale about being fooled. It is a model of how to behave when the universe hands you a number that cannot be true. You do not flinch, and you do not believe too quickly. You measure again, better. So we carry the skeptic's warning forward deliberately because it sharpens everything to come. If a single bright star, close enough to study for decades, could fool the experts into reading it as older than the universe, then a faint galaxy at the very dawn of time, glimpsed through stretched and dust-reddened light, can fool us far more easily and far more thoroughly. The Methuselah star tells us that the most literal, most shocking reading of Webb's data, the reading where stars truly ignited before the Big Bang, is exactly the kind of claim that history says will fall first. And that is the right expectation to hold. But expectation is not proof. To test it, we have to actually go to the edge and meet the galaxies that are wearing this ghost's costume now, starting with the single most distant object that human beings have ever confirmed. Is less than break time equals 1s. Is greater than number. Part 4. Mom Z 14 and the edge of the visible. Let me introduce you to the current record holder, the most distant galaxy that humanity has ever confirmed. A object catalogued with the unlovely name Mom Z 14. It sits at a redshift of 14.44, and that number, once you translate it out of the dry language of astronomy, is genuinely difficult to hold in your mind. We are seeing this galaxy as it was roughly 280 million years after the Big Bang. The universe, when this light left, was under 2% of its current age. If you compressed all of cosmic history into a single human lifetime of 80 years, this galaxy's light set out before the end of the first birthday. We are looking at the cosmic equivalent of the first hours of a very long life. For a long time, simply finding anything at all this early was the achievement. The cosmic dawn, the era when the first stars and galaxies switched on and began to light the darkness, was a theoretical place, a chapter we could write equations about but never photograph. Mom Z14 is a photograph of that chapter. Its light was imaged in 2025, and its distance was not merely guessed from colours, but pinned down by spectroscopy, the gold standard, where you spread the light into its component wavelengths and read the redshift directly. It was then peer-reviewed and published. This is not a rumour or a candidate awaiting confirmation. It is a confirmed record, the new far edge of the visible universe. Now here is where it stops being a triumph and starts being a problem. Look at how small it is. The galaxy has an effective radius of only about 240 light-years. To give that meaning, the Milky Way is roughly 100,000 light-years across, so this object is something like 1% of our galaxy's width. It is closer in scale to a single large star cluster than to what we usually mean by a galaxy. And yet, despite being so compact, it is luminous, bright enough to be seen across the entire observable universe, with a stellar mass comparable to a small companion galaxy of our own, a tiny thing, blazing far brighter than its size should allow, at the very beginning of time. But the size is not even the detail that should unsettle you most. The detail that should unsettle you is the chemistry. When astronomers examined the light of MOM-Z14, they found signatures of carbon and nitrogen. These are not elements the universe was born with. The Big Bang produced essentially hydrogen and helium and almost nothing else. Every carbon atom, every nitrogen atom, every heavier element in existence had to be forged in the nuclear furnace at the core of a star and then released back into space when that star died. For a galaxy at the dawn of time to already contain carbon and nitrogen means that an entire earlier generation of stars must have already been born, lived out their lives, and died, seeding this galaxy with their ashes, all within the first couple of 100 million years. Think about what that requires. To find these elements this early is to find evidence of a generation that came and went before the generation we are actually looking at. It is like opening what you believe to be the first page of a book and finding footnotes referencing earlier pages you cannot see. The enrichment implies a hidden prologue, a round of star birth and star death that had to be squeezed into an impossibly short window near the very beginning. The galaxy is not just present too early. It is already chemically processed, already a second draft, when by every reasonable expectation it should still be a first attempt. Let me hold the honest caveat up now, because I promised we would not hide from it. Some of this galaxy's brightness, the part that makes it look massive, could be inflated by a feeding black hole at its center, exactly the effect we discussed earlier, where light from around the black hole masquerades as stellar mass. We are going to test that mechanism hard in a little while, and it does real work in calming down the worst of these numbers. But notice that the chemistry is a different kind of evidence, and a harder one to explain away. You can argue about how much of the light is stars and how much is a black hole. It is much more difficult to argue away the carbon and nitrogen, because those elements simply are there, and something had to make them. And MOM-Z14 did not appear in isolation. It edged past the previous record holder, a galaxy at redshift 14.18, by a small margin, which tells you something about the momentum of this field. The records are not just being broken, they are being broken in a particular direction, earlier and earlier, and each new record holder seems to arrive carrying the same uncomfortable luggage. Too bright for its size, too enriched for its age, too finished for how little time the universe had to finish it. One such galaxy is a curiosity. A trend of them, each one independently confirmed, is the beginning of an argument. Let me linger on the chemistry a little longer, because once you really grasp it, you cannot unsee it, and it is the part that no amount of black hole accounting can erase. Every atom of carbon in your body, every atom of nitrogen in the air you are breathing as you listen to this, was manufactured inside a star. The universe did not arrive with these elements ready-made. It arrived with hydrogen and helium and a trace of lithium and nothing else of consequence. To make carbon, you need a star to fuse helium in its core over millions of years. To then scatter that carbon out into space, where it can become part of a new galaxy, you need that star to die, often in an explosion that seeds its surroundings with the elements it forged. This is the slow alchemy that built everything heavier than helium, and it runs on the lifespans of stars, which are not short. So when MOM-Z14 shows carbon and nitrogen at 280 million years after the Big Bang, it is telling us that this entire cycle, star birth, star life, star death, and the seeding of a new generation, had already happened at least once before the light we are seeing left the galaxy. There was a prologue. There were stars before these stars, a first generation born from pure primordial gas that lived and died in the dark before the chapter we can actually see. We are not looking at the beginning of this galaxy's story. We are looking at its second act, with the first act already finished and off stage. And the universe simply does not seem to have given it enough time to have a first act at all. So sit for a moment with what this single object represents. Its light has outlived every star you have ever seen with your unaided eyes. It has outlived the constellations, which will rearrange themselves long before this photon's journey could ever be repeated. It travelled for more than 13 billion years across an expanding cosmos to land on a mirror coated in gold, hanging in the cold 1.5 million kilometres from Earth, and the message it carried was not a postcard from a simpler time. It was a problem. The closest thing to the beginning that light will ever let us see, and it is already busy, already working, already a little too far along. A single early galaxy, no matter how strange, could always be a fluke, a 1 in a billion accident that we happen to point our telescope at. The skeptic in us, the one the Methuselah star trained so well, would be right to say so. The case only becomes serious when the impossible thing stops being a single object and starts being a population, when the strangeness repeats itself in forms that are even harder to dismiss. And that is exactly what has happened, because the next objects we have to confront are not tiny enriched smudges. They are enormous, elegant, fully formed spirals, sitting in an era where spirals were never supposed to exist, is less than break time equals 1s, is greater, number. Part 5 spirals that had no time to form. It is one thing to find a bright, compact blob of light at the dawn of time and argue about how much of it is stars and how much is a feeding black hole. It is something else entirely to find a fully organized spiral galaxy with the kind of sweeping, ordered architecture that takes a long, patient history to build. And Webb has found exactly that, more than once, which is why the story we are telling refuses to stay simple. The most remarkable of these has been given a name that suits it, Zhulong, after the torch dragon of Chinese mythology, a creature whose opening and closing eyes were said to bring day and night. This galaxy is a grand design spiral, the most elegant kind, with 2 clear arms winding out from a central hub, and it spans roughly 62,000 light-years from edge to edge. That makes it a genuine near twin of the Milky Way in size and structure. If you saw it floating among our local galaxies, you would not blink. And we are seeing it as it was about 1 billion years after the Big Bang. To understand why that timing is a problem, you have to understand how a spiral is thought to be made. Spiral structure is not something a galaxy is born with. It is something a galaxy settles into, slowly, after long stretches of relatively undisturbed rotation, as density waves ripple around the disk and organize the stars into those graceful arms. A classical central bulge of old stars, a flat rotating disk of younger ones, clean arms tracing through them. This is the signature of a mature, settled adult galaxy, one that has had billions of years to calm down and find its shape. The early universe was supposed to be the opposite of calm. It was supposed to be a chaos of small fragments crashing together, far too turbulent and far too young for anything as composed as Zhulong to exist. And yet there it is, with its old central bulge already in place, its broad star-forming disk already spread out, and its spiral arms already drawn, when the universe had completed less than 1/10 of its present age. The astronomers who study these objects do not hide their reaction. One of them described the experience plainly, saying it is a big surprise how the telescope keeps finding giant and fully formed spiral galaxies further and further back in time. That is not the language of a settled science. That is the language of people watching their expectations come apart in real time, politely, in peer-reviewed journals. Zhulong is not even alone in its strangeness. There is another giant, ordered disk galaxy, nicknamed the Big Wheel, sitting at a similarly early epoch, another full-sized, rotating structure that should not have had the time to assemble. So the Torch Dragon is not a lone freak that we can quarantine and forget. It is part of a small but growing gallery of premature order, galaxies that wear the calm architecture of maturity in an era that was supposed to be nothing but youthful chaos. When the same impossible thing shows up in two different objects, found by different teams, the fluke explanation gets much harder to maintain. And the pattern is not only about shape. Bring in another object, a galaxy catalogued as Sears 2588, which is massive and already metal-enriched, just 400 million years after the Big Bang. Metal-enriched, in the language of astronomy, means full of elements heavier than helium, the same kind of chemical enrichment we met in MOM Z14, requiring the same hidden prologue of earlier stars living and dying. So now we have two different symptoms of the same disease, structure that is too ordered and chemistry that is too processed, both running well ahead of the schedule the standard story allows. The early universe, everywhere Webb looks, seems to be a step or two further along than it has any right to be. Let me make the scale of Zhulong tangible, because numbers like 62,000 light-years can wash over you. Imagine our own Milky Way, the galaxy you live inside, with its familiar pinwheel of arms, the same galaxy whose faint band you can see arching across a truly dark night sky. Now imagine seeing a galaxy essentially like it, that fully realized, that organized, but lit by light, that left it when the cosmos was a small fraction of its current age, when by all rights the universe should have been a junkyard of half-built fragments still learning how to be galaxies. That is the dissonance. Not a strange object you have never seen the likes of, but the most ordinary, recognizable kind of galaxy, showing up in the one place and time where it absolutely should not be. It helps to understand why theorists were so confident that early spirals should be impossible, because their confidence was not arbitrary, it was built on solid physics. In the standard story of how galaxies form, the early universe is a turbulent place where small clumps of matter pull themselves together and then crash into one another, merging again and again into larger and larger objects. Each of these mergers is violent. It throws stars onto chaotic orbits, stirs the gas, and scrambles any delicate structure that might have started to form. A spiral disk, with its stars all orbiting in the same flat plane, in the same orderly direction, is a fragile thing. It needs a long stretch of calm, free from major collisions, for the disk to settle and for those graceful arms to organize themselves. The early universe, with its frequent mergers, was supposed to be the enemy of that kind of calm. It was supposed to tear disks apart faster than they could form. That is why Zhulong is not just surprising but genuinely theory-bending. It is not a small effect at the edge of the error bars. It is a fully realized 62,000 light-year spiral disk, calm and ordered and mature, sitting in the exact era that was supposed to be too violent for such a thing to survive. To build it, you either need the early universe to have been far calmer than we thought, allowing disks to settle quickly, or you need the disk to have had a head start, some scaffolding already in place, that let it skip the slow and dangerous assembly. Both of those explanations, calmer early universe or pre-existing scaffolding, are exactly the kind of radical idea we are going to be forced to consider, and Zhulong is one of the objects pushing us toward them. To be fair, and we are always going to be fair, these early spirals are rare. For every Zhulong, there are many shapeless, chaotic early galaxies that fit the expectations just fine. It may even be that spiral structure was fragile in that era, easily torn apart by the frequent collisions of the young universe, so that the few spirals we catch are fleeting and lucky survivors. But notice that rarity is a clue, not a dismissal. The question is not why there are so few. The question is how there can be any at all, how a single one of them found enough calm and enough time to draw those arms when the clock says there was no such time available. So look at where we have arrived. We started with one tiny, overbright, over-enriched galaxy at the absolute edge of sight. Now we have a small gallery of impossible objects, enormous spirals, and massive enriched disks, each one an independent line of evidence, all of them pointing the same uncomfortable direction. The early universe looks too complete, and completeness is supposed to take time the universe had not yet spent. The weight of these objects, piling up one on another, is starting to bend the timeline in a way that is genuinely hard to ignore. At this point, any honest skeptic in the room should be getting loud, insisting that surely the measurements are simply wrong. And that skeptic is absolutely right to insist on it. So let us give that voice the full and serious hearing it deserves, and try as hard as we possibly can to make all of this strangeness disappear. Is less than break time equals 1s? Is greater than number part 6, the honest debunking. The most responsible thing you can do with an impossible result is to attack it, not to cherish it, not to rush it onto a thumbnail, but to try with everything you have to make it ordinary, to find the boring explanation and see if it holds. This is how science protects itself from its own excitement, and it is exactly what the community did with Webb's impossible galaxies. So for this part, I want you to imagine the most determined skeptic in the room standing up, and I want us to give that skeptic the floor completely, because the case they make is strong and you deserve to hear it at full strength. Their first weapon is dust, the same dust we met when we talked about how starlight is red. Cosmic dust reddens light, absorbing the blue and letting the red through, and a young galaxy seen through enough dust will produce a fingerprint of color that mimics an old, red, ancient population of stars. So the skeptic says, of course these galaxies look old. You are looking at young stars through a veil of soot, and the veil is doing the aging, not the stars. Correct for the dust properly, account for how much of it sits between us and those stars, and the impossibly old ages should slide downward towards something reasonable. Their second weapon is the rhythm of star formation. We tend to assume galaxies build their stars smoothly, but the early universe was a place of sudden, violent bursts, where a galaxy might erupt into furious star formation, fall quiet, and erupt again. When you have a fresh burst of brilliant new stars sitting on top of an older, underlying population, the combined light becomes genuinely ambiguous, and a fitting routine can be pulled toward an age that is far too high or far too low, depending on the assumptions baked into it. The skeptic argues that this bursty, uneven history is exactly what scrambles the age estimates and produces the alarming numbers, and that once you model the bursts correctly, the alarm fades. Their third weapon is the one we flagged with MOM-Z14, the feeding black hole. A rapidly accreting black hole at a galaxy's center surrounds itself with gas so hot it blazes, and that blaze gets folded into the galaxy's total light. A routine that assumes every photon comes from a star will read that extra brilliance as extrastellar mass, making the galaxy appear far heavier and more built up than its actual population of stars would justify. So the skeptic says, you are not even measuring galaxies properly. You are measuring galaxies plus their hidden black holes and mistaking the black hole's light for an overgrown galaxy. Now here is the part where intellectual honesty demands that we hand the skeptic a real victory because they earned it. When astronomers went back and handled these effects carefully, modeling the dust, accounting for the bursts, separating out the black hole light, the worst of the numbers came down. Those original redshift 8 galaxies, the ones whose stars seemed to be 900 million to 2 billion years old, the very objects that gave us our impossible opening, were reanalyzed, and their average ages dropped to around 600 million years. 600 million years sits comfortably inside the time available at that epoch. The stars were not older than the universe. They were young stars, dressed in dust and confusion, that a first pass had mistaken for ancient ones. The institution that runs the telescope put it about as plainly as an institution ever does. In their own public summary of the reanalysis, they concluded that the early galaxies, in their words, were not too big for their britches after all. Much of the apparent overmassiveness, the part that made these galaxies look like they had built far too many stars far too quickly, turned out to be black holes brightening them, not a genuine excess of stars. When you strip the black hole light back out, the galaxies shrink to something the standard story can mostly accommodate. The skeptic, in other words, was largely right about the most extreme claims. So, let me say the uncomfortable thing directly, the thing a less honest version of this video would bury. The cheapest, most literal reading of our title, the reading where actual stars truly ignited before the Big Bang, the reading that opened this whole journey, largely collapses right here. It does not survive careful analysis. The impossible ages were, in the cleanest and best studied cases, an artifact of a difficult measurement pushed past its limits, exactly as the Methuselah star was a generation ago. If we are being rigorous, and we are, then the dramatic headline that started us off has just been taken apart in our own hands, on purpose. And notice how perfectly this rhymes with the ghost we met earlier. The Methuselah star looked older than the universe until sharper data on its distance and chemistry brought it home. These galaxies looked older than the universe until sharper modelling of dust and bursts and black holes brought them home too. It is the same story, scaled up from a single nearby star to the entire frontier of the cosmos. An impossible age, produced by a measurement still settling into focus, dissolving once the focus arrives. History repeated, the ghost laid to rest again. I want to make sure you do not walk away from this part thinking the scientists involved were embarrassed or caught out. The opposite is true, and it matters for how you should read the whole field. The reanalysis that brought the impossible ages down was not a humiliating retraction. It was science working exactly as it should. A first measurement found something startling. The community took it seriously, more data and better models arrived, and the picture sharpened. The fact that the most extreme claims did not survive that process is not a failure. It is the immune system of science doing its job, attacking the boldest claims hardest, letting only what is robust pass through. When you see a dramatic result get walked back like this, you should trust the field more, not less, because it shows the corrections are real and the self-criticism is genuine. This is also why the residue, the part that did not get walked back, deserves so much respect. If this community were in the business of inflating results to chase headlines, they would have clung to the impossible ages and ignored the corrections. Instead, they did the corrections, accepted the deflation, and only then noticed that something still did not fit. A problem that survives that level of hostile scrutiny from the very people who would most like it to go away is a problem worth taking seriously. The skeptics won the first round decisively, and that victory is exactly what makes the second round so interesting. If this video were an honest debunking and nothing more, it could end right here, and the answer to the title would be a clean, satisfying no. Webb did not find stars that predate the Big Bang. It found young galaxies that fooled a first analysis, and a second analysis set the record straight. That would be a perfectly good story, the kind that lets you fall asleep reassured that the universe still behaves. And I would be lying to you if I pretended that comfortable ending were the whole truth. Because here is the strangest thing of all. The thing that keeps this from being a tidy bedtime story with a tidy resolution. The people closest to this data, the very astronomers who did the careful reanalysis, the ones who corrected the dust and subtracted the black holes and brought the worst numbers down, did not relax afterward. They did not dust off their hands and declare the puzzle solved and the universe normal again. They stayed uneasy. And they stayed uneasy for a reason, because when you subtract every artifact, when you remove every overcounted black hole and every misjudged grain of dust, something stubborn is still sitting there in the data, refusing to leave. That residue is where the real story finally begins. Is less than break time equals 1s is greater than number, part 7, the residue. Debunking the worst-case ages did not return the early universe to normal. This is the crucial turn, and it is the one almost every headline misses in both directions. The breathless headlines miss it because they want the impossible stars to be real. The dismissive headlines miss it because they want the whole thing to have been a silly mistake, now safely corrected. Both are wrong. Taking apart the most extreme claims did not restore order. It only narrowed the gap from something obviously impossible to something much quieter and much harder to wave away. Picture what is actually left after the cleanup. Even with the most conservative, careful, skeptic-approved ages, the early cosmos still shows you disks that are too ordered, black holes that are too massive, and structure that is simply too complete for the small amount of time on the clock. Xulong did not get less elegant when the dust was modelled correctly. A 62,000 light-year spiral with old bulge and clean arms is still sitting there 1 billion years after the beginning, and no amount of careful dust correction makes that architecture take less time to build. The chemistry of Mo-14 did not vanish when the black hole was subtracted. The carbon and nitrogen are still there, still demanding an earlier generation of stars. The artifacts were real and worth removing, but they were the loud part of the problem. Underneath them is a quiet part that does not go away. Astronomers have a name for this surviving unease. They sometimes call it the early universe tension, or more informally, the Webb tension, and it is worth being precise about what kind of tension it is. It is not only a tension about mass, about galaxies being too heavy. After the corrections, it is more subtle, and in some ways more profound. It is a tension about time. The universe keeps showing us, at its leading edge, more finished work than the available hours can account for. Not impossibly more, not stars before the Big Bang more, but persistently, stubbornly more. Why does this residue resist the easy fixes that work so well on the extreme cases? Because dust and bursts and black hole light are very good at moving a single number, like an inferred age or an inferred mass. They are not good at explaining a shape. You cannot dust correct your way out of a 60,000 light-year spiral structure. The arms are either there or they are not, and they are there. You cannot subtract a black hole and make carbon and nitrogen disappear. The elements are either present or absent, and they are present. The corrections that tamed the headline numbers simply have no grip on the deeper kind of evidence, the structural and chemical maturity that says, regardless of the exact age, this thing has been working for a while. And then there is the problem of the black holes themselves, which is its own quiet alarm. Webb keeps finding supermassive black holes, objects millions to billions of times the mass of our Sun, already in place when the universe was only a few 100 million years old. Even if you let those black holes feed at the absolute maximum rate that physics allows, the rate at which the outward pressure of their own radiation would start to choke off the inflow, growing one to such enormous size in so little time, is uncomfortably, almost suspiciously, tight. The very black holes that we use to explain away the galaxy's brightness turn out to carry an impossibility of their own. They are too big, too soon, by their own accounting. So this is the precise moment, the hinge of the entire story, where serious physicists stop asking one question and start asking another. They stop asking, what is wrong with the measurement? Because the measurement has been beaten on, corrected, and beaten on again, and the residue survived all of it. And they start asking, instead, what is wrong with our assumptions? Specifically, what is wrong with our assumptions about the clock? Because if the objects are real, and the careful ages are real, and the structure still does not fit, then maybe the thing that does not fit is not the galaxies at all. Maybe it is our idea of how much time there has been, or how time itself began. There are really two different ways the clock could be wrong, and they lead to two very different places, so let me lay them side by side. The first possibility is that our model of how quickly things can form in the early universe is mistaken, that galaxies and black holes simply assembled faster than our theories allow, for reasons we have not yet grasped. The second, more radical possibility is that our number for how much total time there has been is mistaken, that the universe is either much older than we say, or that its beginning was not the clean starting line we imagine. One of these doors leads to a universe far older than the textbooks claim. The other leads to a beginning that was not a beginning at all, a Big Bang that was really a doorway out of something that came before. I want to anchor this with one hard fact, so you understand that the cosmic clock is genuinely contested and not just by dreamers. Right now, there are two excellent, careful, independent ways to measure how fast the universe is expanding, and they disagree with each other at a level physicists call 5 sigma. 5 sigma is the same threshold of certainty that particle physicists demand before they will announce the discovery of a new particle. In other words, the disagreement about the expansion rate is not a rounding error or a sloppy measurement. It is a rock-solid contradiction. And since the expansion rate is exactly what sets the age of the universe, a rock-solid contradiction about expansion is a rock-solid hint that our handle on cosmic time is not as firm as the round number 13.8 would have you believe. It is worth being precise about how unusual this situation is, because tensions like this do not come along often, and when they do, they tend to precede revolutions. Most of the time in science, anomalies are small and lonely. A single measurement looks odd, and either it gets explained away or it sits in a corner waiting for attention, one quiet question mark in an otherwise tidy ledger. What is happening with the early universe is different in kind. It is not one anomaly. It is a cluster of them, pointing the same way, surviving correction, and showing up independently in galaxies and black holes and the expansion rate all at once. When anomalies start to rhyme like that, when several different measurements all lean in the same uncomfortable direction, history suggests you are no longer looking at noise. You are looking at the early signs that a foundational assumption is about to give way. We have seen this pattern before in the history of physics. Small, stubborn disagreements that would not resolve, the orbit of a planet that did not quite match prediction, the color of light from a glowing object that the equations got wrong, turned out not to be minor bookkeeping errors, but the loose threads that, when pulled, unraveled an entire worldview and rewove it into something deeper. Relativity and quantum mechanics both began as the refusal of a handful of stubborn numbers to behave. The residue Webb has left us may be nothing, a set of problems that careful work will eventually tame within the standard picture. Or it may be one of those loose threads. We cannot yet tell, and that uncertainty is precisely what makes this moment so alive. Let me reassure you before we step through either door, because we are about to wander into territory that sounds like science fiction. Everything we are about to discuss is published, peer-reviewed work, defended by physicists with serious reputations, appearing in respected journals. We are not leaving the map. We are following the map to its strangest edges, where the cartographers themselves are arguing about what the symbols mean. Some of these ideas will probably turn out to be wrong, That is how frontiers work. But none of them are crank fantasies, and all of them are honest attempts to explain the residue that the debunking left behind. So here is where we stand, restated as plainly as I can. The literal claim that Webb found stars older than the universe was a false alarm, and we proved it false ourselves. But that false alarm cracked open a real question, and the crack is not closing. The early universe is too finished, and we are left to wonder whether the problem is our model, our clock, or our very idea of a beginning. Let us walk through the first door, the gentler one, and ask what happens to every single impossible galaxy if the universe is not 13.8 billion years old, but nearly twice that. Is less than break time equals 1s is greater than number. Part 8. What if the universe is far older than we think? The simplest way to make a too mature galaxy ordinary is almost embarrassingly obvious once you say it out loud. Give the universe more time. If the problem is that there are not enough hours on the clock for these galaxies to have formed, then the cleanest solution is to find more hours. Stretch the age of the universe, and a spiral at 1 billion years stops being a miracle and becomes merely an early bloomer. And there is a physicist who has tried, in complete seriousness and in peer-reviewed print, to do exactly that, to nearly double the age of everything. His name is Rajendra Gupta, a physicist at the University of Ottawa, and his proposal is as bold as cosmology gets. He argues that the universe is not 13.8 billion years old at all. He argues it is roughly 26.7 billion years old, almost precisely twice the standard figure. If he is right, then every impossible galaxy we have agonized over has had nearly twice as long to assemble itself, and the entire crisis we have been building evaporates into a non-problem. Zhulong had plenty of time to grow its arms. Momsy 14 had plenty of time to forge its carbon. The residue dissolves, not because the galaxies are different, but because the calendar is. Now, you cannot simply declare the universe older because it would be convenient. You have to change something in the physics to justify it, and Gupta's model changes two things, both of which are unconventional, and I want to walk you through them carefully and fairly because they are the kind of ideas that are easy to mock and harder to actually evaluate. The first ingredient is the notion that the fundamental constants of nature might not be constant. We treat certain numbers, the strength of gravity, the way light and matter interact, as fixed pillars that have held the same value since the beginning. Gupta's model allows some of these to slowly drift over cosmic time in a coordinated way, which changes how we translate the light from distant galaxies into distances and ages. He calls this framework covering coupling constants, and the consequence is that the same observations get reinterpreted as coming from a much older, more stretched out cosmic history. The second ingredient is older and, frankly, more controversial, and it carries a name that makes most cosmologists wince. It is called tired light. The idea, in its original form, dates back nearly a century, and it offers an alternative explanation for redshift, the very stretching of light we have leaned on this whole time. Instead of saying that light is stretched because space itself is expanding, tired light proposes that light simply loses a little energy on its enormous journey across the cosmos, growing redder, not because the universe is growing, but because the photon is, in a sense, getting tired. On its own, pure tired light was tested and discredited decades ago because it fails to match a whole range of observations that ordinary expansion explains beautifully. But Gupta does not use it on its own. He combines it carefully with expansion and with his drifting constants into a hybrid that he argues can fit the data while roughly doubling the inferred age. Here is the payoff he is reaching for, and you can see why it is tempting. In Gupta's older universe, The James Webb observations that have caused such a stir become exactly what you would expect rather than a scandal. Galaxies that look too evolved for 13.8 billion years look perfectly normal for 26.7 billion years. The supermassive black holes have time to grow at sensible rates. The mature spirals have time to settle. Everything that we have been calling impossible becomes possible all at once with a single adjustment to the master clock. It is the kind of solution that has a certain elegance, because it fixes many problems with one move, and physicists are always drawn to a single move that fixes many problems. But now I have to give the criticism its full weight, because the response from the broader community has been overwhelmingly skeptical, and the skepticism is well-founded. The age of the universe is not propped up by a single measurement that Gupta could overturn with a clever reinterpretation. It is propped up by many independent measurements that all converge on roughly 14 billion years. The faint afterglow of the early universe, mapped in exquisite detail, points there. The oldest star clusters in our galaxy, dated by completely different methods, point there. The way the lightest elements were forged in the first few minutes of the cosmos points there. To nearly double the age, you would have to explain why every one of these independent clocks is wrong in exactly the way needed to fool us into the same incorrect answer, and that is a very tall order. As one prominent cosmologist put it, there are many, many measurements that suggest the universe is about 14 billion years old, and a single new model does not get to overturn all of them on its own say-so. The tired light component draws particular fire, and deservedly so. It was not abandoned out of fashion or stubbornness. It was abandoned because it makes predictions that the data flatly contradict, predictions about how the brightness and the apparent duration of distant events should behave, predictions that expansion gets right and tired light gets wrong. Reviving it, even in a hybrid form, means taking on all of those old problems and arguing they have been solved, and most working physicists are not convinced the solution holds. So, let me be clear and direct, the way I have tried to be throughout. Gupta's 26 billion year universe is a minority view, contested at nearly every step, and you should not walk away from this thinking it has been established. It has not. And yet, if you stop the story at simply dismissing Gupta, you miss the deeper and more unsettling point, the one that survives even after his specific model is set aside. The point is that the age of the universe is genuinely contested at the edges, and not only by lone iconoclasts. The mainstream itself, the careful, conservative, establishment cosmology, is currently tangled in a disagreement about cosmic time that it cannot resolve, and that disagreement has a name. It is called the Hubble tension, and it has grown serious enough that some researchers have started calling it the Hubble crisis. Let me explain the Hubble tension as simply as I can, because it sits right at the foundation of everything. There are two principled ways to measure how fast the universe is expanding, which is the number that, more than any other, sets the age. The first way works outward from our cosmic neighborhood. You find objects whose true brightness you understand, certain kinds of pulsating stars and certain kinds of stellar explosions, and you use how bright they appear to ladder your way out to greater and greater distances, measuring the expansion as you go. This local method gives an expansion rate of about 73 in the units cosmologists use. The second way works in the opposite direction, from the infant universe outward to us. You take the oldest light in existence, the faint heat left over from when the cosmos was a few 100,000 years old, and you read the expansion rate out of the patterns frozen into it. This early universe method gives an expansion rate of about 67, 73 and 67. They do not sound far apart, but these are not casual estimates with sloppy error bars. They are two of the most carefully constructed measurements in all of science, and each one has been refined and stress-tested for years, and the gap between them has not closed, it has hardened. The disagreement now stands at a level of statistical significance that physicists call 5 sigma. 5 sigma means the chance that this is a random fluke is vanishingly small, the same standard of certainty required to announce the discovery of a fundamental new particle. In other words, the two clocks that should agree on how fast the universe is expanding, and therefore how old it is, are in flat, rock-solid contradiction, and nobody yet knows why. Before we go on, let me make sure the connection to our central mystery is unmistakable, because it is easy to treat the Hubble tension as a separate quarrel happening in another room. It is not separate. The age of the universe, that 13.8 billion years we have leaned on to call Webb's galaxies impossible, is not measured directly. Nobody has a stopwatch that has been running since the beginning. The age is calculated, and one of the most important ingredients in that calculation is the expansion rate, the very number the two methods cannot agree on. Feed in the higher expansion rate, and you tend to get a somewhat younger universe. Feed in the lower one, and you get a somewhat older one. So a 5 sigma disagreement about expansion is not a side issue. It is a disagreement that propagates straight into the age, the headline number, the figure on which the entire premise of impossible galaxies rests. When the experts cannot agree on the expansion rate, they cannot fully agree on the age. And when they cannot agree on the age, the word impossible loses some of its force. And the disagreement is not for lack of effort or care. Both camps have thrown everything they have at their measurements, checking and rechecking, hunting for the hidden mistake that would make the gap close. For years, the hope was that one side simply had an error, a subtle systematic flaw that, once found, would reconcile the two numbers and let cosmology relax. That hope is what makes the next part of the story so important, because the search for that hidden error led directly back to the James Webb Space Telescope, the same instrument that handed us the impossible galaxies in the first place. The telescope at the center of our mystery turns out to be at the center of this one too. And here is the detail that should make you sit up, the place where Webb itself enters the story. For a while, the optimists hoped the Hubble tension was just a mistake in the local measurement, an error creeping in from crowded fields of stars or underestimated dust. If so, it would quietly resolve, and cosmology could relax. Webb was the instrument that could check. With its sharper infrared vision, it went back and re-examined the very stars the local method depends on, the pulsating stars used to build the distance ladder, and Webb confirmed the local number. It did not find the hoped-for mistake. It ruled out the easy explanations, the crowding and the dust, and left the 73 standing firm. By doing so, Webb did not soothe the tension, it sharpened it into a crisis. The same telescope that gave us the impossible galaxies also slammed shut the easiest escape hatch from the disagreement about cosmic time. Now connect this directly back to our question, because the link is everything. How fast the universe expands determines how long it has been expanding, which is just another way of saying how old it is. A faster expansion rate generally implies a younger universe, a slower one, an older universe. So a genuine, unresolved 5 sigma fight about the expansion rate is, underneath, a genuine, unresolved fight about the age of the universe. The very number that every older than the universe headline secretly depends on, the 13.8 billion years, rests on top of an expansion rate that two excellent methods cannot agree on. The floor is not as solid as the textbooks imply. We can feel it flex. Set Gupta beside the Hubble crisis and notice the relationship, because it is subtle and important. Gupta wants to throw out the clock and replace it with one that reads nearly twice as long. The mainstream Hubble crisis does not go nearly that far. It does not double the age. It only wobbles it, revealing that even our best, most conservative measurements of cosmic time are quarreling at the level of percentages, not factors of 2. But both of them, the radical and the mainstream, are whispering the same uncomfortable thing into our ear. The single number that the entire premise of impossible galaxies leans upon is softer, more contested, and less settled than the public is ever told. You do not have to believe the universe is 26 billion years old to absorb the lesson. You only have to notice that the experts cannot fully agree on how old it is, even within the standard picture. I should mention, with a clear warning label attached, that there is a smaller and wilder camp that goes further than anyone we have discussed. These are the thinkers who argue that the redshift we have interpreted as expansion this whole time is partly or wholly something else, that the universe might not be expanding in the way we believe at all. If they were right, the entire foundation of cosmic age and cosmic distance would come undone, and the impossible galaxies would be impossible only because our framework for reading them is broken from the ground up. I want to be honest that this is a fringe position. The mainstream does not accept it, and the weight of evidence for an expanding universe is enormous. But I mention it because it sits at the far end of the same spectrum, the spectrum of doubt about whether we really understand cosmic time, and Webb's results have given that whole spectrum new energy. So let me gather the thread of this part and tie it firmly back to where we are going. Every claim that Webb has found something older than the universe is, when you strip it down, secretly a claim about that one disputed figure, the age of the cosmos. If the figure is simply wrong, as Gupta argues, then the impossible galaxies were never impossible, only misclocked, measured against a calendar that was off by a factor of 2. And if the figure is merely uncertain and contested, as the Hubble crisis shows even the mainstream admits, then we have less right than we thought to call anything impossible at all. More time, in either form, makes the residue shrink. But here is the catch, the thing that keeps this from being the end of the journey. Suppose the figure holds. Suppose the universe really is 13.8 billion years old, the Hubble crisis gets resolved without changing the age much, and Gupta's doubling is rejected for good. Suppose, in other words, that the clock is right and the galaxies are still too mature for it. Then adding time is not the answer, because there is no more time to add. And in that case, we are forced through the second door, the stranger and more vertiginous one, the door where the problem is not how much time the universe has had since it began, but whether it truly began at all. Because if the structure Webb sees did not have time to form inside our universe, perhaps some of it did not form inside our universe. Perhaps some of it was already here, inherited, when the Big Bang lit the fuse, and that idea that there was a before is no longer the exclusive property of mystics. It has become a serious published proposal, and it starts with the possibility that the Big Bang was not an explosion at all, but a bounce is less than break time, equals 1s is greater than. Number, Part 9, The Bounce. A universe before the bang. If adding time to our universe will not fix everything, then perhaps the universe did not start at the Big Bang at all. This is the second door, and I want you to step through it slowly, because on the other side, the meaning of our title transforms completely. Up to now, predates the Big Bang has been a phrase we kept trying to debunk, a measurement error to be corrected. On this side of the door, it becomes something else. It becomes a literal description of a real, physical proposal defended in one of the most respected physics journals in the world. The proposal is called bounce cosmology, and its central idea is disarmingly simple to state. The Big Bang, in this picture, was not the birth of everything from nothing. It was a rebound. Imagine a previous universe, not unlike ours, but contracting instead of expanding, collapsing inward over an enormous span of time, getting denser and hotter and smaller, until it reached some minimum size where it did not crush itself out of existence but instead sprang back outward. That spring back outward is what we call the Big Bang. What we have always pictured as the absolute beginning was, in this view, the turning point of a much longer story, the moment a dying cosmos became a newborn one. Sit with the consequence of that, because it is the whole point. In a bounce, the phrase before the Big Bang is not poetry and not a category error. It refers to a genuine epoch, the contracting phase, a real stretch of cosmic time that truly preceded our expansion. There was a before, it had a history, and crucially, that history could leave things behind, objects and structures that survived the bounce and carried over into our universe, like belongings rescued from a house before it collapsed and carried into the new one built on the same ground. If anything made that crossing, then our universe did not start from a blank slate. It started already furnished. This is where a recent result turns the abstract idea into something concrete and almost touchable. In 2026, a study led by a cosmologist at the University of Portsmouth, working with colleagues at the Institute of Space Sciences in Barcelona, proposed exactly this kind of survivor. They argued that black holes, which formed during the contracting phase, before the bounce, could endure the bounce itself and persist into our present universe. They gave these survivors a name that captures them perfectly. They called them cosmic fossils, relics of a world that ended before ours began, still drifting through the cosmos today, still exerting their gravity, still shaping what we see. Now follow the implication, because it is staggering, and I do not want you to miss it. A black hole that formed in the universe before the bounce and survived into ours would be, by definition, older than the Big Bang, not metaphorically, not as a measurement artifact, as a genuine physical object, one you could, in principle, point a telescope toward, that predates the moment we have always called time zero. After all our careful debunking, after we dismantled the impossible stars and laid the Methuselah ghost to rest, here is a serious scientific proposal in which something truly does predate the Big Bang, and it predates it not by accident of bad data, but by the actual structure of cosmic history. And these cosmic fossils, the authors argue, would not be idle curiosities. They could do an extraordinary amount of work. The same population of pre-bounce black holes could account for dark matter, the unseen stuff that outweighs all the visible matter in the universe and holds galaxies together, a substance we have hunted for decades and never identified. They could contribute to the faint background hum of gravitational waves now being detected rippling through the cosmos. And most relevant of all to our story, they could serve as the seeds from which the early supermassive black holes and the early galaxies grew. The authors put it in a single, almost casual sentence that, once you understand it, is anything but casual. If massive black holes already existed immediately after the bounce, then the early universe would not have to build galaxies from scratch. Read that line again with everything we have learned, and the whole crisis we have been building falls into place. The reason Webb's early galaxies look too finished, too massive, too quickly assembled, the reason their central black holes are too big too soon, is that they were never built from scratch in the first place. They were assembled around seeds inherited from before our universe began, scaffolding carried across the bounce, a head start handed down from a previous cosmos. The galaxies are not racing to build everything in a few 100 million years. They are decorating a frame that was already standing when our universe was born. The impossible timeline becomes possible the moment you allow that the construction did not start at zero. There is a question you should be asking right about now, because it is the obvious one, and the bounce has an answer for it. How could anything possibly survive the bounce itself? If the previous universe contracted down to an almost unimaginable density before springing back, surely everything in it would be crushed and obliterated, melted into a featureless soup with no memory of what came before. And for ordinary matter, that is largely true. But a black hole is not ordinary matter. A black hole is a region where gravity has already won so completely that it is sealed off from the rest of the universe behind a one-way boundary. It is, in a sense, already the densest thing that can exist, a pocket of collapse that the surrounding collapse cannot further destroy. The proposal is that black holes, precisely because they are already extreme, could ride out the bounce intact, while everything around them was remade, like stones that survive a flood that washes away the soil. If that is right, then the bounce does not start the new universe completely from scratch. It starts it salted with survivors, a scattered population of black holes inherited from before, already massive, already gravitating, already capable of pulling gas and stars and smaller objects toward them. And that changes the entire timeline of galaxy formation. In the standard story, galaxies must build their central black holes from small seeds, slowly, over hundreds of millions of years, which is exactly the process that seems to run out of time. In the bounce story, the big black holes are already there at the starting gun, so galaxies can begin assembling around them immediately, skipping the slowest and most troublesome step. The very problem that Webb keeps handing us, structure that is too built up too early, is precisely what you would expect if the construction had a head start that began before our universe did. I have to be careful and honest about the status of this idea, because it would be easy to oversell it, and I have promised you I would not. This proposal is published in a respected, mainstream physics journal, and it is led by a serious, established cosmologist. It is not fringe in the way that plasma cosmology or pure tired light is fringe, but it is a minority view, one proposal among several competing attempts to explain the early universe, and it is far from confirmed. There is, as yet, no direct detection of a cosmic fossil black hole, no smoking gun that would settle the matter. It is a beautiful, rigorous, testable idea that might well turn out to be wrong. What it is not is a fantasy. It is real physics, taking the residue seriously and following it somewhere remarkable. Let me give you one image to carry out of this part, because it captures the strangeness better than any equation could. We have spent decades searching for dark matter, building detectors far underground, smashing particles together, scanning the sky, hunting for some new, undiscovered fundamental particle to explain the invisible mass that shapes every galaxy. And this proposal whispers a different answer. What if the dark matter, quietly holding the cosmos together, is not a new particle at all, but the cremated remains of an entire previous universe, a population of black holes that formed in a world that died before ours was born, survived the fire of the bounce, and have been steering the dance of galaxies ever since. Every spiral arm, every cluster, every galaxy Webb photographs, gently herded by the ghosts of a cosmos that came before. And distinguish this clearly, one last time, from the genuine fringe, because the distinction is what makes it powerful. This is not a denial that the Big Bang happened. The bounce does not erase the Big Bang. It reinterprets what the Big Bang was, transforming it from a creation event, a beginning from nothing, into a transition event, a doorway between one cosmic phase and the next. The bang still happened. It just was not the start of the story. And if it was a doorway, then Webb, peering as far back toward that doorway as light allows, might be photographing the furniture that came through it. But a bounce is not the only way to put a universe before our own. There is a second route to the same astonishing destination, proposed by one of the most celebrated minds in the history of physics, and it claims that the oldest light in the sky still carries the faint handwriting of a universe that came before. Is less than break time equals 1s is greater than number, part 10. Penrose's previous Eon, where the bounce imagines a single universe contracting and rebounding, Roger Penrose imagines something even grander, an endless chain of universes, each one flowing smoothly into the next. Penrose is not a fringe figure. He is a Nobel laureate, one of the most decorated mathematical physicists alive, a man who helped lay the foundations of how we understand black holes themselves. And late in a long and extraordinary career, he has been arguing for an idea so strange that it would be easy to dismiss if it came from anyone else, and so carefully constructed that it cannot be dismissed lightly coming from him. He calls it conformal cyclic cosmology, and the picture it paints is this: the universe does not have a single beginning and a single end. Instead, it consists of a sequence of what Penrose calls eons, each one a complete cosmic lifetime. Each aeon begins with its own Big Bang, expands, forms galaxies and stars and life and black holes, and then continues expanding forever into a cold, dark, empty future. And here is the strange and beautiful turn. That infinite, frozen, empty end of one aeon becomes, by a mathematical sleight of hand that Penrose makes rigorous, the fiery Big Bang beginning of the next. The death of one universe is the birth of another, not through a violent collapse, but through a smooth and almost gentle continuation. The trick that makes this work is subtle, and I want to give you the intuition rather than the mathematics, because the intuition is genuinely lovely. In the far, far future of a universe, after the last stars have died and the last black holes have evaporated away, there will be essentially nothing left but light, photons drifting through an endless dark. And in a universe with nothing but light, something peculiar happens to the very notions of size and time. Light does not experience the passage of time, and with no massive objects left, there are no clocks and no rulers, nothing to measure scale against. In that strange final state, the difference between infinitely large and infinitesimally small, between unimaginably old and freshly born, stops being meaningful. The cold, infinite, empty end becomes mathematically indistinguishable from a hot, tiny, brand new beginning, and so the end of one aeon simply becomes the Big Bang of the next, the universe forgetting its scale and starting over. Now, an idea this audacious needs evidence, and Penrose claims to have found some, written into the oldest light in the sky. The faint heat left over from our own Big Bang, the cosmic microwave background, the same ancient glow we have leaned on to measure the age of the universe, is supposed to be almost perfectly smooth, a near-featureless wash of warmth across the whole sky. But Penrose argues that it is not perfectly smooth. He claims it contains faint, circular features, slight rings of structure, and he gives them a name that connects them directly to the universe before ours. He calls them Hawking points. The reasoning behind that name is worth understanding, because it ties two of physics' greatest ideas together. Stephen Hawking showed that black holes are not truly black, that they slowly leak energy and, over almost incomprehensible spans of time, evaporate away entirely, releasing all their mass back into the universe as a faint hiss of radiation. Penrose argues that in the previous aeon, the universe before ours, supermassive black holes would have finished this evaporation, dumping their enormous energy into the dying cosmos. And when that aeon's empty end became our Big Bang, those concentrated points of released energy would have carried over, smeared out by the transition into faint circular patches in our microwave sky. Each Hawking point, in this telling, is the fossil signature of an entire supermassive black hole that finished dying in the universe that came before ours. Penrose has continued to push this, and a recent piece of work from 2025, done with a collaborator, examined the angular size of these supposed Hawking spots in detail. They found the spots appear to be about twice the size that the simplest version of the theory predicted, and rather than abandoning the idea, they argued this larger size could be explained by gravitational wave effects crossing over from before the transition, refinements layered onto the original claim. The program is alive, in other words, still being developed, still being argued for by one of the sharpest minds physics has produced. It is worth appreciating just how much Penrose is willing to give up to make this idea work, because it reveals the kind of mind we are dealing with. Almost every cosmologist accepts that the very early universe underwent a brief, explosive episode called inflation, a fraction of a second of staggeringly fast expansion that smoothed the cosmos out and planted the seeds of all later structure. Inflation is one of the load-bearing pillars of modern cosmology, and Penrose, more or less, wants to do without it. In his picture, the smoothness that inflation is invoked to explain comes instead from the orderly, low-disorder state inherited from the dying end of the previous aeon. He is proposing to replace one of the most successful ideas in cosmology with a previous universe. That is not a small adjustment. It is a wholesale reimagining of where the order in our cosmos comes from, and it is part of why the reception has been so divided. You cannot casually accept Hawking points without also accepting that much of the standard origin story is wrong. What I find genuinely moving about the proposal, whether or not it survives, is the picture of memory it offers. In Penrose's universe, nothing is truly lost. The supermassive black holes that dominate a dying eon do not simply vanish when they finish evaporating. Their energy, their influence, the faint imprint of where they were, carries across the boundary into the next universe and gets written, however faintly, into the new sky. It is a cosmos with a kind of inheritance, where each universe is shaped in subtle ways by the one that came before, a chain of worlds passing faint signatures down an endless line. Whether or not the data supports it, it is one of the most poetic ideas in all of physics, and it comes from one of its most rigorous practitioners. But I have to give you the controversy at full strength, because here it is fierce, and honesty demands it. Most cosmologists are not convinced by the Hawking points, and the objection is statistical and serious. When you have an enormous, noisy map of the whole sky, faint circular patterns will appear in it purely by chance, the way you can find shapes in static or faces in clouds. Independent teams have reanalyzed the same microwave data and concluded that the supposed Hawking points are entirely consistent with ordinary random fluctuations once you account properly for how many patterns you would expect find by accident. In their view, the rings are not messages from a previous eon. They are the mind and the statistics, finding pattern in noise. So, conformal cyclic cosmology remains at best a contested and unproven idea, defended brilliantly by its creator and doubted by most of the field, and I present it to you exactly that way, a live possibility rather than an established fact. And yet, hold it next to the bounce for a moment and notice the remarkable thing they share. Bounce cosmology arrives at a universe before ours by contraction and rebound. Conformal cyclic cosmology arrives at a universe before ours by an endless smooth chain of eons. They start from completely different physics. They were built by different people for different reasons, and they disagree on almost every detail. But they arrive at the same destination. Both say that there was something before the Big Bang, and both say that the something could have left traces in our universe, whether as surviving black holes drifting through the dark, or as faint rings written into the oldest light. The structure that Webb sees at the edge of time, too finished and too soon, might be carrying a memory older than our own beginning. Whether that memory is a relic black hole seeding a galaxy, or a ghostly ring in the ancient sky, the phrase predates the Big Bang has stopped being a headline error. In these frameworks, it has become a serious, if unproven, physical claim, and that transformation from error to claim is the real discovery hiding inside our title. But before we let ourselves be swept all the way into a universe that predates itself, intellectual honesty demands that we turn around and face the opposite answer, the answer that says the entire question is a mistake, that there simply was no before at all. Is less than break time equals 1s is greater than number, part 11, or maybe there was no before. For every theory that places a universe before the Big Bang, there is another that says the word before, in this context, is simply meaningless. This is the answer that refuses the premise of the question entirely, and it comes not from skeptics trying to be difficult, but from some of the most careful thinkers in physics, including Stephen Hawking himself. They would say that asking what came before the Big Bang is not a hard question with a hidden answer, It is a malformed question, like asking what lies north of the North Pole. The most famous version of this is called the no-boundary proposal, developed by Hawking together with James Hartle. Their idea is that as you trace the universe backward toward its beginning, time gradually stops behaving like time and starts behaving more like another dimension of space. Near the very origin, the sharp distinction between time and space softens and blurs until there is no longer any clean moment you could point to and call the first instant. The universe, in this picture, has no edge, no boundary, no abrupt starting line. It is smooth and self-contained, finite in the past, but without a beginning in the way we usually mean. The way the surface of the Earth is finite but has no edge. You could fall off. The South Pole image is the one to hold, because Hawking used it himself and it is perfect. Walk south and keep walking south, and eventually you reach the South Pole, and once you are standing on it, the question what is further south has no answer. There is no further south. You have not hit a wall or an edge. You have simply run out of the very direction the question depends on. The no-boundary proposal says that asking what came before the Big Bang is exactly like this. Travel back toward the beginning, and you eventually run out of before, not because you hit a barrier, but because the direction itself, the past, gently ceases to exist. There is no before, in the same way there is no further south, and the absence is not a mystery to be solved, but a feature of the geometry. There is a second way to dissolve the before, and it comes from the idea of eternal inflation, which most cosmologists take seriously as a description of the very early universe. In this picture, the brief, explosive expansion that kicked off our cosmos was not a one-time event. It is still going on somewhere, endlessly, in a larger arena beyond our horizon. Our entire universe is just one bubble that formed and stopped inflating inside a far larger space that is still inflating furiously and will go on doing so forever. In that framework, there is no single global beginning you could point to for everything. There are only bubbles, endlessly forming, each with its own local Big Bang, inside an inflation that may have no start we can identify. Our beginning is real and local, but it is not the beginning of all things, because there may be no such thing to be the beginning of. There is something almost vertiginous about these no-before answers, and it is worth sitting with the discomfort rather than rushing past it. We are built to think in terms of causes and sequences. One thing happens, and then because of it, another thing happens, an unbroken chain stretching back and back. When you ask a small child where something came from, and then where that came from, you eventually arrive at the Big Bang, and the child quite naturally asks what came before, because the chain of before has never once failed them in their whole short life. The no-boundary proposal is the deeply strange claim that the chain has an end that is not a wall. The links simply stop being links, smoothly, with nothing missing and nothing cut off. Our intuition has no slot for that, because nothing in ordinary experience behaves that way. And yet, the mathematics permits it, even prefers it, and that gap between what the mathematics allows and what our intuition can hold is one of the most humbling things in all of science. Notice, too, that the no-before answers do something subtle to our original question that is easy to miss. They do not say the impossible galaxies are not there. They simply locate the strangeness somewhere other than a hidden prior cosmos. If there was no before, then Webb's too early structure cannot have been inherited from a previous universe, which means it must have formed inside ours, fast, by some process we do not yet understand. So the no-before answer is not a way of making the mystery disappear. It is a way of insisting that the mystery lives in our physics of the young universe, rather than in the metaphysics of a beginning. It trades one kind of strangeness for another, and which kind you find more comfortable may say as much about you as about the cosmos. So now hold all three pictures up together side by side, and feel how strange our situation really is. There is the bounce, in which a previous universe contracted and rebounded into ours, leaving fossils behind. There is the endless chain of eons, in which our Big Bang is the smooth continuation of a dying predecessor, written faintly into the oldest light. And there is the no before, in which time simply rounds off at the origin and the question dissolves, or in which our bang is one bubble among endless others, with no global start at all. These are three profoundly incompatible answers to the same question, and right now, with the evidence we have, we cannot choose between them. One telescope, a handful of impossible galaxies, an unresolved fight about the cosmic clock, and three irreconcilable stories about the beginning with no verdict in sight. It can feel unsatisfying to be handed three answers and told that nobody knows which is right, but I would ask you to see it differently. The fact that we can even pose these as physical questions, the fact that a bounce or an aeon or a smooth no-boundary origin can be written down as mathematics and tested against the oldest light in the sky, is itself astonishing. A few centuries ago, the question of what came before the beginning belonged entirely to priests and philosophers, answerable only by faith or by argument. Now it belongs, at least partly, to telescopes. We have dragged the deepest question about the origin of everything out of the realm of pure speculation and into the realm where data can have a say, even if the data has not yet spoken clearly. That migration from myth toward measurement is one of the quiet triumphs of the whole scientific project, and Webb is one of its newest instruments. And that, strange as it sounds, is the honest place to stand, so let me make the value of it plain. These know-before ideas are the necessary counterweight to everything that came before them in this video, the gravity that keeps us from floating off into pure speculation. Webb's too early structure tempts us, powerfully, toward a universe that predates itself, toward bounces and aeons and surviving relics. But a fair investigator has to keep firmly in view the alternative that the beginning really was the beginning, that there was no before to inherit anything from, and that the strangeness Webb has shown us lives entirely in our incomplete models of how fast a young universe can build itself, not in some hidden prior cosmos. We do not get to pick the answer we find most thrilling. We only get to hold all of them honestly and wait for better evidence to narrow the field. And so we come, at last, to the question of what Webb has actually given us, if not an answer. Is less than break time equals 1s, is greater than number, part 12, the doorway. We began with a single galaxy that read as older than the universe, and we are ending at the edge of the oldest question a mind can ask, whether the universe had a beginning at all. That is the arc of this whole journey. And before we let it go, I want to retrace it honestly, the way you would retrace your steps at the end of a long walk to be sure of where you have actually been. We started with the cheap, shocking version of the claim, the one where Webb found stars that ignited several 100 million years before the Big Bang, and we did not protect it. We took it apart ourselves, with the same tools the astronomers used, the dust that reddens young stars into looking old, the violent bursts of early star formation that scramble the clock, the feeding black holes that brighten galaxies into looking heavier than they are. The literal claim dissolved in our hands, just as the Methuselah star dissolved a generation ago when sharper data brought its impossible age home. If that were the end, the answer to our title would be a clean and comfortable no, and you could sleep easy. But it was not the end, because something survived the debunking. After every artifact was removed, a residue remained, quiet and stubborn and real. Spirals too ordered for their age, galaxies too chemically enriched for the time available, supermassive black holes too large too soon. The corrections that tamed the loudest numbers had no grip on the deeper evidence, the structure and the chemistry that say, whatever the exact age, this early universe has been working for longer than the clock admits. That residue is the real discovery, And it is what turned a debunked headline into a serious question. And that question opened two doors, and we walked through both. The first door asked whether the universe is simply older than we say, and there we met Gupta's contested doubling of cosmic time, and more soberly, the mainstream Hubble crisis, the 5 sigma disagreement that shows even careful cosmology cannot fully pin down the age. The second door asked whether the beginning was a beginning at all, and there we met the bounce, with its cosmic fossil black holes that are older than the Big Bang by the literal structure of cosmic history, and Penrose's endless eons, with their ghostly rings of light from a universe before ours. And then, as a counterweight, we met the idea that there was no before at all, that time rounds off smoothly at the origin and the question itself dissolves. I will not stand here and declare a winner, because the honest truth is that nobody can, not yet. The evidence that reopened the question cannot close it, but weigh the candidates one last time and feel their pull. A universe with a doubled clock. A universe rebounding from a prior collapse, furnished with relics. An endless chain of universes, each born from the cold death of the last. Or a single self-contained cosmos, with no before, where the strangeness is only our ignorance of how fast a young universe can build. 4 answers, all serious, all incompatible, all alive. Notice how much the meaning of our title has shifted over the course of this walk, because that shift is the real journey we have taken. At the start, Predates the Big Bang meant a measurement error, a galaxy that fooled a first analysis into reporting an impossible age. We proved that meaning false. But by following the residue honestly, the phrase transformed under our feet into something else entirely, a literal description of objects in serious published physics, a relic black hole that survived a bounce, a ring of light from a previous aeon, the same 4 words that began as a debunked headline, ended as a real, if unproven, scientific possibility. We did not arrive at a different answer to the original question. We arrived at a deeper and more honest version of the question itself, which is often the most a genuine mystery will give you. Of all the images we have gathered, the one I cannot put down is the cosmic fossil, the possibility that the dark matter holding every galaxy together, the invisible mass we have hunted for decades and never named, might be the surviving embers of a cosmos that ended before ours began. That when Webb photographs a too-perfect spiral at the dawn of time, it may be photographing the handiwork of those embers, structure herded into shape by the ghosts of a previous universe, without ever knowing it. We built an instrument to look back as far as light would let us, and it may be showing us not the first chapter of our story, but the last sentence of someone else's. I want to come back, for a moment, to the honesty we promised at the very start, because it is the thread that has held this whole journey together. We did not protect the exciting answer, we attacked it. We took the headline that stars formed before the Big Bang, and we dismantled it ourselves, with dust and bursts and feeding black holes. And we watched it fall apart exactly as the Methuselah star fell apart a generation ago. If you remember only one thing from these 2 hours, let it be this. The most literal version of the title is almost certainly false, and the people who study this for a living are the ones who showed it to be false. That is not a disappointment. That is the discipline earning your trust. And yet here we are at the end, and the question has not closed, because honesty cut both ways. The same rigor that demolished the cheap answer also refused to let us pretend the residue was not there. We could not, in good conscience, debunk the headline, and then quietly ignore the spirals that are too ordered, the chemistry that is too processed, the black holes that are too large too soon, the expansion rate that 2 great methods cannot reconcile. Honesty does not get to stop once it has comforted you. It has to keep going even when it makes you uncomfortable again. And that is how a debunked headline turned, by the end, into one of the most open and serious questions in cosmology. So let me tell you what Webb actually did, because it is subtler and larger than the headline ever was. It did not prove that the universe predates itself. It did something more profound. It reopened the oldest question in human thought, the question of the beginning. And it did so not with philosophy but with data, by showing us a cosmic dawn that was busier, more finished, more advanced than the beginning has any right to be. It took a question we thought we had answered, filed away under 13.8 billion years, and quietly pried the file back open. And do not lose sight of the galaxies themselves in all this theory, because they are the ground truth that started everything and that everything must answer to. MOM Z14 is really out there, tiny and luminous and laced with carbon, at the edge of what light can show. Zhulong is really out there, a near twin of our own galaxy with its arms already drawn, sitting in an era that was supposed to forbid it. These are not thought experiments. They are confirmed objects, photographed, their distances measured, their light real and arriving. Whatever the right answer turns out to be, whether a doubled clock, or a bounce, or an aeon, or simply a young universe that builds faster than we understood, that answer will have to explain these specific, stubborn, actual galaxies. The theories may come and go, but the galaxies are not going anywhere. They are the fixed points around which the whole debate must turn. Think about the strangeness of what we have done as a species. We took a 6.5-meter mirror, coated it in a breath of gold, folded it like origami, and flung it 1.5 million kilometers out into the cold, beyond the moon, to a place no human has ever gone or can go, and we told it to look back toward the beginning of time and report what it found. And it looked as far as light itself allows, all the way to the edge of what can ever be seen. And what it found waiting for us at that edge was not an answer. It was a question about whether there is an edge at all, about whether the beginning was ever the right word for what we have been calling the beginning. The light is still arriving, every night, older than our theories and patient with our confusion, carrying messages we have only begun to learn how to read. Somewhere in it may be the signature of a universe before this one, or the smooth and seamless rounding off of time into its own origin, or simply our own ignorance reflected back at us. We do not yet know which. But we are looking, and the looking itself, the act of sending a golden eye to the edge of time to ask whether time has an edge, may be the most extraordinary thing this small and curious species has ever done.